This cool little device is the Smart Spot Welder from Fnirsi. It's called the Fnirsi SWM-20 and it has a max output of 1200 amps, which sounds pretty crazy considering the size. I've always thought that to have a decent spot welder, you'd need big car batteries and massive cables, which feels a bit overkill if all you want is to build a few batteries for your long-range drones. Fnirsi is a company that makes a range of electronic tools, and they're not that well known here in Norway where I live, which is a bit surprising because my first impression of this one is really good. It's small and compact, it has a bright 2.4-inch TFT display, it's rechargeable, and it comes with a 5000 mAh battery, which you can also use as a power bank. Everything you need to get started is included, including a set of spare welding tips. According to the user manual, you can perform up to 1500 spot welds on a single charge. So, join me in the process of assembling a 6S2P lithium-ion battery for FPV drones. And just to be clear, this is not a tutorial. I'm not an expert in building batteries. This video is simply you watching me build a battery. I will most likely do things wrong, but I'm counting on you to let me know in the comments section. Even though this is my first time testing a spot welder, I have built a few battery packs before. But back then I used a soldering iron and soldered the batteries directly, something I got quite a lot of feedback on in a video I made about a year ago, saying that it's not really the right way to do it. So now I'm really looking forward to trying it properly with a spot welder instead, and seeing how much cleaner and more reliable the result will be. The pack I'm building now, I plan to use on a Moz 7V2 frame. The batteries I've built before have a form factor that doesn't really fit well, and they end up sticking out on the sides. Now I'm planning to build them more like these iFlight full-send batteries, with the cells tilted forward in a horizontal layout. This makes the battery a bit longer, but gives a much better fit overall. The cells I'm using are Sony VTC 6 cells. Each cell has a capacity of 3000 mAh and a maximum discharge current of 30 amps. In a 6S2P configuration, that gives me a total of 6000 mAh and a maximum discharge of 60 amps. Why am I using these, you might ask? There are definitely better cells on the market. The reason is simple. I get these for free. They come from decommissioned Makita batteries that I've taken apart and tested. In most cases, it's actually the BMS that fails, while the cells themselves are still perfectly fine. So even though there are better cells out there, I still get around 15 to 20 minutes of flight time with these, and that's more than enough for me. Since I'm a spot welder newbie, I want to do a few tests before I start building the actual pack, just to figure out what power setting I need to get a solid weld. Out of the box, everything is set to the lowest setting, and as you can see, that's not nearly good enough. There are 4 main settings you can adjust. You've got the preheat pulse, which warms up the electrodes and softens the material you're welding. Then there's the interval, which helps prevent the electrodes from overheating. You also have the continuous spot count, where you choose how many welds are made each time you place the electrodes down. And finally, the pulse, which is the most important setting of them all. The pulse setting controls how strong the weld will be. If it's too weak, the nickel strip won't properly bond to the battery. If it's too strong, well, you'll burn through the nickel strip and just end up with a hole. As you can see, I quickly work my way up to a setting of 50 milliseconds since both 10 and 20 didn't give any bond at all. At 50 milliseconds, it's better, but still not quite good enough. I try increasing the preheat to 8 milliseconds, and now it looks like things are starting to come together. The weld is strong enough that I need pliers to pull it off, and when I do, it's the nickel strip that gives way, not the weld itself. I figure I'll just get started and adjust things as I go. It's also possible the positive terminal on the battery will require a slightly different setting. To help keep the cells in place while I'm gluing and spot welding them, I've made these 2 little jigs. I'll drop links to these, the spot welder and the other gear I'm using in the video description. Since I'm building a 6S2P battery, that means 6 cells in series, with each one paired with a parallel cell. Before starting, I've checked that all the cells have the same voltage, and I've labeled them with cell numbers. This part is really important. You don't want an uncontrolled balancing current when you connect the cells in parallel. To glue the cells together, I'm just using regular hot glue. I've seen some people use spacers between the cells to improve heat dissipation, and that probably makes sense, but I'm trying to keep these battery packs as compact and lightweight as possible, so I'm choosing not to do that. I don't glue the cells in the middle, since those are the ones that need to fold toward each other to get that low-profile layout, and on top of the glue, I'll also be wrapping the whole battery pack with tape at the end. Now I'm ready to start spot welding the cells together, so the nickel strip I'm using is a 27mm wide, 0.15mm thick strip, pre-cut for 2 P battery packs, which I trim to fit the layout I want. On the positive terminals, I'm using protection rings. I think they're called fish paper rings. They help prevent any short circuits between the positive terminal and the rest of the battery, since the entire cell, except for the positive terminal, is negative. I start by spot welding the part that will become the inside of the battery, the section that's going to be folded inwards later. This spot welder doesn't have a button or a foot pedal you need to press to weld. It does it automatically, which is actually pretty convenient. It just welds when it's ready. I don't really have a fixed plan for how many welds I need per battery terminal, but my thinking is, the more the better. So if you actually know what's ideal here, feel free to drop a comment and let me know. I'm actually a bit nervous about making mistakes here. I really don't want to accidentally spot weld a short, if that makes sense, so I'm using tape to make sure that doesn't happen. The spot welder is definitely keeping up so far. It has a temperature sensor that warns you if it starts to overheat. Right now, it's showing 31 degrees, so everything is fine. I'm still kind of surprised by the quality of this thing, especially considering it only costs around $50 US. One thing I realized you really need to watch out for. If you're using cells that have been used before, make sure to properly clean and trim the terminals. Any leftover material needs to be removed. Otherwise, you can run into issues like this. What happened here was I actually burned right through the nickel strip, and I think the reason was that it was sitting on top of some leftover nickel that I hadn't removed properly. It definitely made me jump a bit, but it's not really dangerous. You just get a few extra sparks. Alright, this is the last nickel strip before I move on to soldering the balance leads and the XT60 cable. Now I've set the continuous contact points to 2 on the spot welder, so I get 2 welds per contact point. I've also lowered the pulse setting to 40, which reduces the risk of burning through the nickel strip. Now all the cells are spot welded together. I've got positive and negative at opposite ends, so one of the XT60 leads will be a bit longer than the other, but that should be fine. I'm using a multimeter to double check the voltage, just to make sure it's roughly where I expect it to be, which should be around 20 volts, since each cell was at about 3.5 volts. Now, it's time to solder on the balance lead. For a 6S pack, it has 7 wires. The easiest way is to start at the main negative terminal, then attach one wire to each cell, working your way across until you reach the last wire, which goes on the main positive terminal. Now, I'm pre-tinning the points, where I'll solder the balance wires, one for each cell. The red wire on the balance lead goes to the main positive terminal on the battery, so I start at the opposite end of the plug, which is the main negative. Then I sort the wires, based on which side of the battery they need to go. This whole balance wire process can be a bit confusing to watch, and it's kind of hard to show properly on video since there are so many wires. But the key thing is, like I said earlier, one wire for each cell, and it's definitely worth double checking everything because it's a pain having to open the pack again later to fix it. The length of the wire sticking out on the right will determine the length of the balance wire coming out of the battery, so I make sure to adjust it the way I like it. I find it's a hassle when it's too short. For a bit of protection, where the balance lead crosses the nickel strip of another cell, I use some Kapton tape underneath. Kapton tape is a heat-resistant tape made from polyamide film. It's widely used in electronics and technical projects because it can handle extreme heat without melting or losing its properties. I finish all the wires on this side of the battery first, since this is the side that will be folded together. To isolate the two parts of the battery that will be folded together, I use something called fish paper. Fish paper is an electrical insulation material made from compressed fiber. It looks a bit like stiff cardboard, but it's much more durable and heat-resistant than regular paper. You don't want these sticking out too much on the sides because that would create a sharp edge right in the middle of your battery pack. Now, it's time to fold the two parts of the battery together to get the battery pack into the shape I want. It will always end up a bit uneven, but I just press it together, and it will settle later once I wrap the battery with heat shrink. My main concern when building battery packs this way is the bend that forms in the nickel strip. It looks fine, and it shouldn't put any extra stress on it once the pack is fully wrapped. Before I continue and finish the balance lead, I wrap the entire battery with Kapton tape. Now, after folding the battery, you actually have to use your head a bit when soldering the rest of the balance wires because everything is flipped upside down and backwards. So, now, there are only the main positive wire and the main negative wire left on the balanced lead. I'm leaving those for later until I've attached the XT60 cable to the battery. Earlier, I made an XT60 lead with the connector already attached at the end. Since the positive terminal is at the front and the negative is at the back, the negative wire ends up being longer. To attach the XT60 cable, I made these tabs out of nickel strip, I spot weld them on and bend them back so I can solder the wires onto them more easily without soldering directly onto the battery cell terminals. After this, I do the same on the other end, on the positive side of the battery. Afterwards, I have space to solder the final balance wires. So now the battery is basically finished. I'll wrap it once with electrical tape and then add heat shrink over it afterwards. But first, I'm going to connect it to the charger and check that the balance wires are connected correctly and that everything looks good. It's reading all the cells, and the charger would clearly warn me if any of the balance wires were connected wrong or something wasn't right. Before I heat shrink the battery, I wrap it in tape first. I use cloth tape on the ends and regular electrical tape for the rest. I also add a bit more fish paper in the middle to help straighten the pack since it's slightly uneven because of the bend on the nickel strip. Now we move on to the most difficult part of building a battery pack, getting a clean and tight heat shrink finish. The heat shrink I'm using is 130mm wide and has a diameter of 83mm. It could probably have been a bit smaller, and it likely would have given a cleaner finish. But it didn't turn out too bad. Add a couple of cool stickers on it and it'll look even better. As you can see, this form factor fits much better. The weight is more centered towards the middle of the quad and it makes the battery easier to mount. This is especially true for frames that are narrower than the Moz 7 frame, like the SpeedyBee Mario 8 frame. So, thanks for watching the video. Feel free to drop a like if you enjoyed it. I'm planning a video where I test this battery and then open it up afterwards to see how it's holding up, so subscribe if you don't want to miss that. When it comes to the Fnirsi Spot Welder, I can definitely recommend it for projects like this, especially considering the price at around $50 US. I'll leave a link in the description. And remember, always be careful with batteries. I store mine outside the house when they're not in use, and I never charge them without keeping an eye on them. Take care.